Hi, my name's Yuriy and I'm a maths PhD student at Imperial College London, as well as a tutor at the Elite Prep. Today, I'm going to be continuing with the series where I solve quantitative research interview problems, and the problem that we'll handle today is one of Jane Street's monthly puzzles. If you haven't tried them already, I really recommend going on their website, which I'll link below, and just using these for a bit more practice. The problem which we'll handle today is called sum of square. The problem states the following. A circle is randomly generated by sampling 2 points uniformly and independently from the interior of a square and using these points to determine its diameter. What is the probability that the circle has a part of it that is off the square? Give your answer in exact terms. The intuition for this problem is the following. Here, very kindly of them, they've provided some examples already of the situation which we're interested in. In particular, we have these 5 squares where the circle is extruding the square. So what happens is we end up sampling a red point uniformly from the square, a blue point uniformly from the square. Both of them are independent. And then we construct a circle from this red point and blue point, and we want to see if there's any part of the circle constructed which is outside of the square. Okay, so now that the problem should be clear in our minds, we can continue with some hints. So the first hint I would give, they have asked us what is the probability that the circle has a part of it that is off the square, and the hint is to look at the probability that a circle constructed in this way is contained fully inside the square. The second hint I would give is that considering the points on the diameter may not be the most useful way. So I would recommend to think of other ways of uniquely characterizing the circle. And finally, you should keep symmetry in mind in this problem. So that last one is a little bit vague, but it should be clear after some thought. Okay, if you haven't tried the problem yet, I really recommend you try it with these hints before proceeding. If you already have, then we can continue to the solution. To start off with, I will introduce some notation, and it will be helpful if I draw a diagram whilst I am introducing it. So we're always going to be considering the square. We're going to denote this square by S, and we're just going to assume that the square has a width of 2L. In the problem, this should cancel out anyway. So we're assuming the square is equal to this, i.e. it has width 0 to 2L and height 0 to 2L, if we embed it in a coordinate system. Additionally, we are going to, if we consider any 2 points x and y, and if we construct a circle which goes through x and y such that it's the diameter, x and y form the diameter of the circle, then we're going to denote such a circle which is constructed as CXY. Similarly, so if I just copy this, then if we have a point on the diameter, let's call it x, and if we have another point, but now rather than being a point on the diameter of the circle, we're going to say this point is called C, and it's going to be the center of the circle, then we're going to construct the circle which has center C and point on its circumference x. This uniquely characterizes the circle. Such a circle is going to be denoted as C tilde x C. So now C tilde is constructed from a point on the circumference and the center, Meanwhile, C is constructed from 2 points on the diameter. Finally, one other piece of useful notation is going to be y of xc. Let's say y tilde of xc. And this is going to be the point on the circumference of the circle, which is an extrapolation from x through c. So it's exactly like this. If we have an x on the circumference, a center c, then y is going to be diametrically opposite to x through c. So this is going to be y tilde xc. With all this notation, we can now approach the problem. So I'm going to copy this square again. So remember that we're considering the complement of the event. So if the event E is equal to that the circle CXY is not contained inside S, then we want we want the probability of E, but we're going to look at the probability of E complement. So we want probability of E complement. So therefore E complement is equal to CXY belonging to our square S. CXY is just the constructed circle. Okay, so we're going to now write the probability of E complement is equal to the probability that CXY is contained in the square. This is just equal to the probability, and actually instead of little x, little y, let's write big X, big Y to denote that they're random variables and they're uniformly distributed. Then this is just equal to the probability that C tilde, so now it's a circle constructed from the center and a point in the circumference, C tilde X tilde. I'm denoting X tilde because it's going to have the same law as X, but it's not going to be the same random variable. So we're now changing the probability space, and I'll explain how, because it's important. C tilde, X tilde, and a little c. Actually, let's write big C, but not curly c's, so that we still have a random variable for the center, is a subset of the square, but we're also conditioning on y tilde of x tilde c being inside the square. Because there's a one-to-one correspondence between circles which are constructed from 2 points of diameter which are inside the square, and circles which are constructed from a center and a circumference, and such that both the points of the diameter are inside the square. So, because as an example, we could have, for example, had a center here, point X here, but that is not a possible situation, because then we would have had y tilde xc here, so we could not actually have sampled this circle. So that's not possible. So that's why here we need to condition on this event y tilde xc is inside the circle. The next important thing is that we can actually consider these x tilde and c as independent and uniformly distributed. The reason for this is because we have a one-to-one mapping between circles CXY and C tilde XY, C tilde X tilde C, and when we've done that, we have that each Y tilde is corresponding to exactly one Y. So when we're conditioning on this additional fact, we still have uniformness. Great. Now that we're trying to evaluate this, we can do the following. We can use the symmetry argument. So far we've done two things. We've converted from looking at, we've used hint one in essence, where we've converted from looking at the event to the complement of the event. And we've also done this kind of change of variables from looking at the points on diameter to the circle center and the point in circumference. Next point is to use symmetry. So now we're going to split up the square into octants, and we're going to label them O1, O2, all the way through to O8. And we're going to now consider breaking up this final probability, which we've computed, into a condition on each of the octants. So the condition which we're going to have is that the center, if it's in one of the octants, it cannot be in another octant. So we're going to condition on the center being in a specific octant. So we're going to apply, in particular, the law of total probability. We're going to say that star is equal to the sum from I equals 1 to 8 of the probability of this C tilde X tilde C being inside the square, given that Y tilde X tilde C is contained in the square, and that C is contained in the ith octant. This is multiplied by the probability that C is contained in the ith octant, given Y tilde X tilde C is in the square. That's just the law of total probability. And by symmetry, we have that each of these values is just equal to 1 over 8. Then we also have that each of these values, so it's equal to 1 over 8 because C must be in at least one of the octants. The conditional probability won't matter in the end because we just have a sum over all of the disjoint events, so we're still going to have a probability of 1, and because we know that each of these events is the same, each of them must have probability 1/8. These probabilities must all equal to the same thing but with the first octant. So all of this ends up being 8. So 8 times this for the first octant, so this for the first octant, so changing this I to 1, and times 1 over 8. So that just equals to this with the first octant. That's equal to probability C tilde X tilde C is a subset of the square, given Y tilde X tilde C is in the square, and that the center is in the first octant. Okay, so now we have to evaluate this. By the rules of conditional probability, this is equal to probability of C tilde X tilde C and intersected with the event that the extension Y tilde is still inside the square, conditioned on C, divided by the probability of just the extension being inside the square, conditioned on C. This is just conditional probability. Now, the key to notice, if the constructed circle from a center and a point on its circumference is already fully inside the square, then since Y tilde is on the circle, it must also be inside the square. So this event, Y tilde X tilde C is in the square, is actually just a subset of C tilde X tilde C being in the square. And that means that this last probability is equal to, okay. So we now just need to evaluate both of these conditional probabilities on the center being inside octant 1. The way we can do that is by considering, in each case, the joint distribution of x tilde and c. And we're going to actually fix a specific c in the first octant. And then we're going to see when this event happens. So, for example, when c tilde x tilde c is inside the square, and when y tilde x tilde c is inside the square. So in other words, we're going to be looking at the integral, and because now c is uniform, we're going to be just looking at the probability when we're conditioning on c. So c now is, because we're conditioning on c being in the first octant, we have c in O1, and we also have probability that c tilde x tilde c is a subset of S conditioned on c equals c. So that's kind of formal notation. So integrated with respect to c. And in denominator, we have the same, just for y tilde xc being in the square. So what we want to find is these densities. Well, going back to our diagram, let's consider this first octant. So we're only considering this area here. And let's choose a center C. So we're fixing that center. And once we've chosen this C, if we denote C is equal to x, y, then we know that y must be less than x if we're considering the square as a coordinate system, and also that x is between 0 to L, because the width of the square was 2L, and y is, so that's the region. Y is less than or equal to x, and x is in 0 to L. Then the probability that we select a value x, actually a value x tilde as I've been denoting, such that this c tilde x tilde c is a subset of the square, is just the probability of finding a c which is inside this circle. I'll explain in a second. Because if we have a c which is outside of this circle, an x tilde which is outside, so here if we choose x tilde, for example, this is still okay. We're right on the boundary. We would then, from this c and this x tilde, construct a circle which is still inside the square. As soon as we go past the boundary, however, then the circle is by definition not inside the square. Now, the same would happen if we were to choose a point anywhere further away than the distance from C to the closest point to the boundary. And that closest point is exactly Y, because the closest boundary to C, because we're in first octant, is the lower boundary. So that's the first circle. We're going to denote the area of this circle as R1 of C, because we fixed a center C. The next question is to see when y tilde x tilde c is inside the square. So when the extension is inside the square. Well, if we have another point, which is, so when we select another x tilde, for example, so if we take x tilde to be here, then we would have to extend all the way through C and along the same vector, extend the same distance all the way across to the other side. So we know if we look at the boundary here, so if we look at this boundary and this boundary, that we can only go twice as far as how far we've gone to x. Sorry, as how far we've gone to C, the center. So I'm going to now draw this in green. So if C is at x, we're going to go to 2x horizontally, and because y is the height to C, and we know that the red circle was of radius y, the top barrier, the top boundary of the green square will coincide with, will be a tangent to this circle. So this length is 2y, and the bottom length, so the width, is 2x. The reason why we can't have the point x tilde being anywhere here, for example, is because if we draw a line from x tilde here through to C, then y tilde x tilde C would be outside of the square. So that's not the situation which we want. We want it to be inside the square. And also the x tildes are also sampled from inside the square. So when you're looking down here, you cannot go further than the barrier, so that's also fine. Okay, so in total, we have a region of y less than x. X is in 0L. We have that the probability of C tilde x tilde C being a subset of S, given C equals C, is just equal to R1 of C. And up here, I'll denote the green square as R2 of C. R1 of C was just equal to pi times y squared, because that's the area of this circle. Similarly, the probability of y tilde x tilde C being inside S is equal to R2 of C, and that was just the area of the square. So that's equal to 4xy. So finally, we just need to compute the integrals of each of these. So if this was dagger, then dagger is equal to the integral over this region. So from x from 0 to L, y from 0 to x, of pi y squared dy divided by integral over the same region but over 4xy dy dx. That's equal to pi over 3 and the integral of 0L x cubed dx, and divided by 2 of the integral of x cubed dx. So this is just equal to pi over 6. So we have that the probability of our event complement is equal to pi over 6. And so the probability of the event that we want is equal to 1 minus pi over 6. So that was the Chain Street monthly puzzle. Thank you very much for watching, and I hope to see you in the next one.